Now that we have looked at limits at infinity and at finite values of functions, we can look at what they mean for the graphs of these functions. So, by a discontinuity, we mean a value x equals x0, where the function f is not continuous. One type of discontinuity we have seen is the missing point, as in example 1 in the previous section. This means there where this point 3,5 was missing. For us, the most important type of discontinuities are the poles, as we have seen them in the examples 2 and 3 in the previous section. We say x0 is a pole if the function diverges to plus or minus infinity as x approaches x0. And we distinguish for poles between such with sign change and such without sign change. Well, we have actually these four possibilities here. Function 1 and function 2. These are functions with sign change in the sense that from here, from the left, it diverges to plus infinity, while from the right, it diverges to minus infinity, and here vice versa. Here, for f3 and f4, it both times diverges to the same infinity, so here both times to plus infinity, here both times to minus infinity, so then we talk about a pole without sign change. If we have a pole at the value x0 here, then we have a vertical line x equals x0 that is a vertical asymptote of the function f. The definition of the asymptote, and here when we write plus minus, we also mean it's sufficient that one of the two is true. So we have a vertical asymptote x equals x0, like here, if the function f of x diverges to plus infinity or to minus infinity when it approaches the x value x0 here. So it doesn't have to be on both sides diverging. It could be even in theory on one side not diverging. Typically it is diverging on both sides. Then we have horizontal asymptotes, as we see here. This means we have a line y equals q, q here 1. This is the case, we have a horizontal asymptote, if the limit of f going towards plus or minus infinity is q. The function value goes towards q, so the graph approaches this horizontal line y equals q. And then there is a third type of asymptote, slant asymptote, as we see it here. Here the graph of f approaches this slant line here, and it gets closer and closer to it without ever touching it. The definition here is that the difference between the value of the function and the value of the line here becomes smaller and smaller as we go to the right. They get closer and closer. The difference between their y values goes towards 0. That's what's expressed in here. What is important to understand is that vertical asymptotes describe the behavior at some finite value x0, somewhere sort of in the center of the function. So here, wherever, at some finite point. While horizontal and slant asymptote describe the behavior of the function as we go off with x towards plus or minus infinity. By the way, we can also rewrite this condition for the horizontal asymptote that we said its limit of f of x for x going to infinity is equal to some value q. We can just say the condition is the limit of f of x minus q is 0, and now we have actually the very same structure as we have for the slant asymptote, just in the sense we take the difference between the graph and the asymptote, and well, in this case, the horizontal asymptote is just one value q. One more specification, we say that the graph, that the line is an asymptote if the graph approaches it more and more, it gets infinitely close to it, but never touches it or never meets it. Well, actually, that's not correct. It means that from some point on, it will never meet or touch it. For example, look here, the graph here, it meets the asymptote, but then it doesn't meet it anymore. So to the right of this point, it doesn't meet it anymore, so it's fine. Or it also, with the slant asymptote here, it cuts this asymptote, but when you look here, it just gets closer and closer. And so from a certain moment on, actually from here on, it will never touch it anymore, not meet it. As a counterexample, take the function sine of x divided by x. You remember sine of x is just this wave function, and now by dividing it by x, when I look now for x going towards plus infinity, it means it will just get smaller and smaller, but it will keep its wave structure, so it will always cut or meet the x-axis, and that means the x-axis is not a asymptote of this sine of x divided by x. How do we find discontinuities and asymptotes? The idea is for horizontal and vertical asymptotes, we just look at the behavior of the function f as x goes towards plus and minus infinity. We analyze it, and by that way we can find whether there is an asymptote, whether the limit goes towards a function. No, that's not the way I want to say it. Either the limit is of the function is a fixed value. So for example, 7, then we know y equals 7 is a horizontal asymptote. Or we see that the difference between the function and a line goes towards 0, then we know that that line is the asymptote. We'll look at that in some examples right in a moment. To find discontinuities and vertical asymptotes, well, we typically look now at functions where the function contains an expression that has a fraction, and where there is an x in the denominator. So we look at values where the denominator becomes 0. So this value, we call it x0, and then we inspect what happens with the function when x approaches the x0, because that's where it is not defined. Let us look now at example 1. We're given this function y equals 2x minus 5 divided by x minus 3, and we want to find and classify the discontinuities and asymptotes of it. And once we've done that, we want also to find its zeros and then provide a sketch of it. So first, find its behavior at infinity, and hence find out whether it has horizontal or slant asymptotes. Stop the film, and here comes the solution. The limit of f of x when x is going towards plus or minus infinity, well, we can actually see directly that it is 2, but if you've forgotten the rule here, we can also do it explicitly as shown here. So we find the limit for f of fx for x going to plus and minus infinity is 2, and this means that we have a horizontal asymptote y equals 2. Now let us find what is the value of the discontinuity. Are there discontinuities? Stop the film, and here comes the solution. We find that the solution, the discontinuity, we find it by setting this denominator x minus 3 equal to 0. We find out there is a discontinuity at x0 equals 3. Now we want to classify it. This means we have to investigate the behavior of the function f close to the value x0 equals 3. So try that on your own, as we have done in the before, and here comes the solution. When we look at the limit for f of x when x is approaching 3 from the positive side, we insert that in here and we find the numerator is actually 1, the denominator is 3 plus, so something larger than 3 minus 3, so we get something larger than 0, so but small, so the whole thing goes off to plus infinity. Now we have to look also at the limit x going towards 3 minus, and again the numerator is still 1 when we insert 3, and when we insert here for the x something a little bit smaller than 3, when we subtract 3 from it we get something a little bit smaller than 0, so we get 0 minus, so 1 divided by 0 minus means the limit goes or diverges to minus infinity. So now we can classify the discontinuity. What is it? Well, and it is a pole, and we have there what type of asymptote? We have a vertical asymptote, namely with the equation x equals 3. Okay, last but not least, we should now find the zeros. How do we find the zeros? We have to set the function value y equals to 0. Well, 2x minus 5 divided by x minus 3. When we set that equal to 0, we get that actually that's the same as only setting the numerator to 0, because a divided by b equals to 0 can only be 0 if a is 0. So we get that x is 5 divided by 2. So we get the 0, 5 halves, 0. And now we can draw the whole, or sketch the graph. We have the 0 here at 5 halves, 0. We have the two asymptotes. Here the horizontal asymptotes y equals 2 and the vertical asymptotes x equals 3. And we know that when we approach the vertical asymptote 3 here from the positive side, we come from we get to plus infinity, so it'll look something like this. So it has to look like this, and from the negative side it looks something like this. So we get this picture here. In example 2, let us find and classify the discontinuities of this function here. So find the discontinuity, stop the film, and here comes the solution. Well, we find the discontinuity by setting 2x plus 2 equal to 0, and we get x equals minus 1. So now we need to inspect the behavior of the function near x equals minus 1. Do that on your own, stop the film, and here comes the solution. When we look at x going towards minus 1 of f of x, when we insert the minus 1 in here, we see we get 0 as well as 0 in the denominator, so we get 0 divided by 0. Well, as we said before, this means this has to be factorizable with x minus minus 1, so x plus 1. So let's do that. Let's rewrite here this as x plus 1 times x minus 3. Here we factor out the 2. Now we can cancel out the x plus 1, and we find out that the limit for x going towards minus 1 is minus 2. Well, what does this mean for the classification of the discontinuity? What type of discontinuity do we have? Can you try to precise it? Here comes the solution. What we have is a missing point, and its coordinates are minus 1, that's the x-coordinate, and its y-coordinate, where it is missing, is the minus 2 here. Here the x minus 1, and here this limit is then the y-coordinate. Now we can rewrite this function f as we did before, as consisting of two parts. Try it on your own, stop the film, and here comes the solution. F of x is undefined if x is equal to -1, and otherwise f of x is just 1/2 x minus 3/2, this here. And so we can sketch now the graph of the function, and we get, sorry, here this straight line just with a missing point here. Just to a reminder how to sketch a straight line, use the y-intercept minus 3/2 and then draw it by going 2 to the right and 1 up. That's then the gradient. Example 3, let us find the discontinuities and asymptotes of this function here. And let us start with the limits, the behavior at infinity. So are there horizontal or vertical asymptotes or slant asymptotes? Well, when we look at this expression, we see when x goes to infinity, this part here will go to 0. So we suspect that this is the slant asymptote. Why is this the case? Well, as I said before, the f of x, here this goes to 0, so what remains is 1/2 x plus 1. This is a straight line. Now we can just formulate to show it. Look at the difference of this function value and the function value here of the line. So f of x minus L of x. So this here minus this here, well, what remains is exactly the 1 divided by 2 minus x, and that goes off to 0 when x goes towards plus or minus infinity. Next, let's look at the discontinuities. Try to find the discontinuity and its behaviors. Stop the film, and here comes the solution. Well, to find the discontinuity, we have just to look at this expression here, 1 divided by 2 minus x. So the 2 minus x has to be 0. We find a discontinuity at x equals 2. And now investigating its behavior there, the behavior of the graph there, or of the function, this means let x go towards 2 plus and towards 2 minus. So let's first look just at the blue part. So x is going towards 2 plus here. When we insert 2 plus in here, what we get is 1 plus 1. And here 1 divided by, and now 2 minus x. When the x is a little bit larger than 2, I have 2 plus. So I get 0 minus. I get a negative number, a little bit smaller than 0. Well, 2 plus this going towards minus infinity, so the whole thing goes off to minus infinity. Now I was too lazy to rewrite the whole thing, so I just used another color and added the minus here, saying now let's look at x going towards 2 minus. Well, here 1 plus 1 remains unchanged, and now if the x is a little bit smaller than 2, then 2 minus this x is positive, so I get 1 divided by 0 plus, so then it goes off to plus infinity. So what type of discontinuity do we have? Well, we have a pole with a sign change, and this means we have a vertical asymptote there. So pole with sign change at x equals 2 and the vertical asymptote at x equals 2. And now we can sketch the graph. Sketching the two asymptotes first, we have the vertical asymptote at x equals 2. We have our slant asymptote y equals 1/2 x plus 1. And then we know when we approach the x from the positive side, when we approach the 2 here from the positive side here, the function value goes off to minus infinity, so it goes down. And when we approach it from the negative side, the 2 here, so 2 minus, it goes off to plus infinity. So probably the graph looks something like this. And that's it.